All right, welcome back to, I think this is our 4th year of Buzzword Bingo. And the intent of the whole thing is for us to be able to field your questions about acronyms and tech stuff that you hear that's like, what are they talking about? So we always start out with a few starter terms, but anyone who calls out a term for us to translate gets one of these fabulous prizes. And if any of you call out something that none of us know, like if you stump the chumps, grand prize this year of a bag full of Microsoft software and stuff.
That's the grand prize.
That is the grand prize. So here's who we have with us. Steve Reynolds with Comcast, really good consumer video guy, set-top box guy, Mr. Video. Jay Rolls, CTO or what is your title now? CTO of Charter. He was on the early, I was almost going to say you invented the internet, but he sent one of the earliest emails in the world, right?
Making that claim doesn't get you very far.
You sent the first bulk email ever, right?
So you claim.
You invented spam.
Lewis Williamson with Time Warner Cable, a fellow engineer, who his claim to fame is he figured out how to put video over fiber optic cable. It's a very big deal. Lewis, one of my favorite people, you can pay me later. And far at the end, the wireless guru of the universe, Tim Burke with Liberty Global. So between everything there is to think about in telecom technology, we have it covered. So we'll start with, has anyone heard of this one? HEVC H.265. Yeah? Anyone hasn't heard of it? That's what we're looking for. Okay. Who wants to go on that?
Mr. Video. I guess I'm Mr. Video, so I get that one. HEVC is the high-efficiency video codec. A lot of you have probably heard of MPEG-2 and MPEG-4. MPEG-4 was a first-generation video compression technology. It was followed up a couple of years later with MPEG-4, which some people also refer to as AVC, which is the advanced video codec. HEVC is the next step in that lineage, and it actually applies an even higher degree of compression to video in order to make bigger video fit into a smaller pipe. And it's something that will be coming our way over the course of the next 2 or 3 years, allowing us to increase the number of channels and indeed send higher quality video over smaller pipes, which means across Wi-Fi and things like that to get it out to IP endpoint devices.
Right, and if you've heard about some of the bandwidth constraints, problems with 3D television and what's coming 4K television, this will help with that too. So that's H.265. Anybody? You get prizes if you throw one out. Dash. Oh. MPEG Dash, another video question.
Actually, what Dash is there's a couple of adaptive protocols out in the market today. Apple uses one that they call HLS, which is HTTP live streaming. I always use these acronyms and I have to think of what they really mean, and sometimes you can use different letters for them. But they have HLS, which is HTTP live streaming. Microsoft has smooth streaming, and there's ways that those are technologies that are used to transmit a lot of the traffic you see over the internet, streaming to, as you heard earlier, Roku and those types of devices. Dash is actually a standard that has come about that is trying to take those two protocols and put it in yet another one that's common. So there's one streaming protocol that you could use across all devices. So it's an attempt to standardize the adaptive streaming protocols over the internet.
And who wants to talk to how adaptive streaming got started, like why it's even happening in the first place? Adaptive bit rate.
There's a couple reasons why the adaptive bit rates became popular over the internet, especially over the top providers. And the way adaptive works is when you encode, you actually encode multiple versions of the same content at different bit rates. The other thing you do is you chunk it up into these small chunks that are delivered over HTTP protocols. And the advantages of using all of this at once is if you get over a noisy a network, you know, wireless is probably the classic one that a lot of people run into. You can't guarantee a high streaming rate all the time. So these protocols are designed to say if my video isn't looking good at, you know, 3.5 megabits, I'll drop down to 2 megabits or 1 or whatever it is. So if you notice adaptive protocol, sometimes you'll see the quality changes as they try to adapt to their network. The other thing they do is they use HTTP to request the stream to say, hey, my network's sucking right now, you know, give me something lower, or hey, I got a lot of bits, give me something higher. And HTTP is used because most of the routers and things in our homes, that port is open, so it goes through routers without you are going to have to configure it yourself. So it's easy for the consumers to use that. It makes it simple and easy for them.
And it also, but for the over-the-top video company or services like Netflix and Hulu and Amazon Prime, you know, the other side of it is it kind of behaves like a gas. If there's this much room, it will, you know, those bits from those providers could take all of the available space because they'll say like, oh, it's clean, let's send the biggest chunk. So it kind of goes both ways.
Yeah, I think in the earlier days it was really about the varying broadband speeds and
Right.
overcoming some of the slower broadband speeds. I think today it's actually more dealing with Wi-Fi as sort of the weak link in the chain, because people are really demanding more and more out of their Wi-Fi as they take the iPad out in the garden and wonder why it's not working. So.
Okay, next one I'm going to throw in is Title VI video. This one tends to come up in the context of, you know, every time you turn around, somebody thinks they can put a video server at the edge of the network and call themselves a cable operator or a multi-channel video provider. And the thing that always stops them is, well, are you Title VI? Steve?
So Title VI refers to a section of the Communications Act of 1934. I know this is what you came here to hear today.
34 or 96?
It's the Communications Act of 34 actually specified the titles that cover wireline services. In 1996, as Jay points out, a new title was added, and it was Title VI, and it was intended to cover regulation for the cable industry. So when we talk about Title VI video, what we're really talking about is all of the federal rules that cable operators have to live under in order to deliver regulated video services. And so that covers.
It's like closed captioning,
Yep.
emergency alerting. It's like all the crap that they have to do.
Well, we don't think of it as crap. We
not
like to think of it as the valuable services that we provide to our customer base. But it really is, you know, all of the things that the federal rules say we have to do as cable providers. And as Leslie points out, that covers some really important things like emergency alert, for example, closed captioning certainly, and other elements of the Americans with Disabilities Act.
Okay, shout them out. Harry, Sue?
Let's see, electronic binary coded information.
Oh, wait a minute, he's using the internet, that's not fair.
I'm going to give you a
You can have a frisbee.
frisbee just for trying. Monetization with regards to digital files. Wow. I'm impressed with my audience today.
Yeah, so there's auctions coming up that the federal government is trying to sell some of the airwaves and have them available for use. And typically, you know, mobile operators own the spectrum, and they own it for themselves, and they can control it for a period of time that they've bought in an auction, so to speak. And we're running out of a lot of spectrum, and so they're trying to auction some spectrum areas that are more for everybody to use, kind of like Wi-Fi. So Wi-Fi operates at 2.4 gigahertz and 5.8 gigahertz, and everybody can use them. It's kind of like the Wild West. You know, anybody can operate in that space, and devices operate in that space. And so they're setting up auctions in white spaces, which is, you know, much down lower than the 2.4 gigahertz and 5.8 that Wi-Fi is at, which stands for wireless fidelity, by the way. But and that's the white spaces in what, the 500 to 600 megahertz spectrum, and they're very small slivers of spectrum that that are being used. But when they're not being used, they want to allow people to operate in those frequencies in the white spaces. So there's a lot.
Are there purple spaces?
Not that I
Blue,
know of.
any
They
other-
should have those, but yeah, just unoccupied pieces of spectrum, and sometimes it's in pieces in portions of time, and you have to look and see if anybody's using it, and you back off, and then you don't use it, and then if you want to transmit, then you go and you transmit on it. So.
When we draw our charts, it's the white space between the graphs.
Between the frequency bands.
Who asked the quantization question?
Quantization is really turning analog signal into a digital signal, because even though, well, at least the younger generation thinks everything is digital, it is an analog world. All of the outputs are really analog. But if you take any signal, whether it's a voice signal or a television signal, you can digitize it using an analog to digital converter, and it will convert it to bits. And if you sample at a certain rate, you can reproduce that by going through the reverse process of digital to analog conversion. So that process of going from analog to digital is called quantization, and that's how we turn the signals, signals and information into digital, and then do the reverse, so they can see it or hear it or operate machinery. We use it for lots of things like that. Store material on hard drives.
Let's talk a little bit about DOCSIS 3.1. How about you, Jay?
Okay, so DOCSIS 3.1, it's easy to tell, is the next version of DOCSIS.
After 3.0.
I think that it's a little bit of a misnomer. This is my personal opinion, that it's called 3.1. It probably should be called 4.0, but I think the industry wanted to make it abundantly clear that we weren't going to be forklifting all of our 3.0 gear when we came out with this new standard. So, hence the 3.1. But it's got a lot of stuff under the hood that's new, and will give us some more bandwidth and give us some more capabilities. And most interesting to me, I think, is that it will start to get rid of what I call the 6 megahertz picket fence, which is that we tend to put everything in 6 megahertz slots, which is based on the old analog methodologies of how we send signals to analog TVs. So it lets us start to get away from there and fill those white spaces.
Those white spaces.
Curious about twisted light technology and how that will be implemented in the cable industry.
Twisted light technology.
Twisted light here. Let me see if I even get this one right here. I believe it's a technology where what they're trying to do is take light and actually modulate it in different planes to increase the density of optical communications there. So right now, I don't know how we would. I don't know of any plans to use it in cable. But cable operators, all of us, we own vast cable networks, or vast optical networks, is what I was trying to say. And we do adopt all of the, or most of the optical technologies when they become prime time, because we try to make most efficient use of our capacity, whether it's over our HFC, or over our coax plant or our optical plants. We adapt those technologies when they become practical there. So.
All right, so these are two of the things that are under the hood of DOCSIS 3.1. And it's great for me because as a person who translates technology, this is all about modulation, or part of it's about modulation. So there's amplitude modulation, frequency modulation in the AM or in the analog world. And then there was this QAM, right? You've heard of it, quadrature amplitude modulation. It's been around for, it made you sound smart at first if you could say like, yeah, I need 3 QAMs for VOD. But now it's just like it's getting boring. So now we've got a new mouthful jargon modulation term, orthogonal frequency division multiplexing. Say that at a cocktail party. They will think you're so smart.
Or they'll make you leave.
Or they'll make you leave. And then,
Yes.
and then the other one is low density parity check, which I spelled that wrong, but low density parity check is the other one. And so when you put these two things together inside DOCSIS 3.0, the 3.1, the assumption is that operators can ring another 50% capacity in the downstream and upstream direction. So it's a big, big, big deal. I guess I did that one.
Yeah.
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 Is there a question?
Yeah. In the back.
AMI 3.0.
AMI or ADI?
Oh, ADI.
You almost stumped the chumps.
So ADI refers to the Cable Labs specifications for moving around metadata associated with VOD content. So there are new versions of that are coming out, actually have already been rolled out, that the industry is moving towards that'll allow us to use richer sets of metadata and richer sets of content as we distribute that to the VOD servers.
All right.
PKI.
I just looked this up this morning. Public key infrastructure, yes!
That's right.
Debbie.
CODF. CODF.
Code orthogonal division multiplexing. Coded? No?
Oh my God, we might have a.
Boy, yeah, CODIF, boy, I can't remember what CODIF stands for, but CODIF is the format that Cable Labs put together, that format as well to describe interactive assets. And so back in the days when we were doing a lot of eBIF work, you actually had to describe the packages that you were going to be inserting into the into the in-band transport, and CODIF was the metadata format that was put together for that.
Content definition format.
Content definition format, there you go.
All right, so did she stump the chumps?
We couldn't
No?
remember the acronym.
No?
Yeah.
Okay, he got it. All right. Web R
WebRTF,
T
RTC.
C.
I'm not the web guy. I know a web guy,
The stumps have been chumped.
but and your reward is a bag of Microsoft software.
I don't know what that one is.
I got one for Jay. I'm not going to play around. He needs to know this stuff. KLAD.
KLAD, K-L-A-D, which is short for key ladder, and that is for those of you that may be familiar with what Cablevision did when they eliminated the cable card from their boxes. There's part of the embedded secret that's in the boxes that their conditional access system is able to take advantage of is based off of a hardware key ladder that is embedded inside the silicon, and that's what KLAD is. So.
Good one. All right, I'm going to step in with 4K. Has anyone seen or heard of 4K video? It's pretty impressive, right? So when you first, he says in the back, when I first saw HD, my first reaction was, this is better than my eyes can see. And now they've taken HD and made it twice as good yet again, or maybe even more than twice as good.
More than twice as good, yeah, because it's 4,096 pixels in the horizontal direction and 2048 pixels in the vertical direction. So it's 4 times as many pixels as you would get off of the highest end 1080 sets today. So yeah, the information transmission is quite a bit better in terms of what the picture quality looks like. Unfortunately, that also comes with a requisite increase in the amount of bandwidth required to transmit it, which is going all the way back to the beginning, why HEVC is something that we're all working on right now in order to be able to squeeze those 4K pictures down through the existing pipe.
And
by the way, they're working on 8K too, so if you
and
think
didn't you guys do a 16K at
super,
Olympics?
We did, yeah.
That was 16, right?
Yeah, it was 8K. What we did at the Olympics was 8K. There were demonstrations that were set up across the country. Some of you might have gone to the ones in New York or Washington, but we were actually showing live 8K content. So
I wish I had seen that.
it's pretty amazing.
Yeah, because I heard it was like you walk up to it and you can see the facial detail of people sitting in the crowds. Like it's that clear. And also, it has been branded now by the Consumer Electronics Association Ultra HD. So if you hear that, that's what people are talking about. And it'll also probably be a very big thing at the upcoming Consumer Electronics Show in January. I'm expecting we're going to see 4K everywhere. Yes?
Anything on the timeline for 4K content?
4K, you know, I was just talking to some content guys last week, and they're not into it because, you know, maybe some cameras exist, but all the other stuff you need behind it to convey and the trucks and all that stuff is Not yet there, so no, not a lot of action.
Sony's got a Blu-ray player that'll convert that 8K, right?
Yeah, and that's probably where you'll see 4K and 8K come out first, is on physical media. You know, it's easier to transmit those discs when you put them on a piece of plastic and put it in your Volvo. So that's where you'll probably see it first, is on physical media.
I was going to say, until we get HEVC and OFDM with
LDPC.
Yeah, with LDPC, yeah.
No one has the bandwidth to carry it.
How soon can this reach the gaming industry?
How soon can
The
4K
4K?
reach gaming?
There are already game developers that are working in 4K. You'll actually see a lot of this stuff on high-end video monitors before you actually see it on televisions. I think LG actually has already rolled out a 4K video monitor that'll probably be used for PC gaming before it's used for anything else.
Yeah, I think the other place where I hear about it is for movie theaters. They're trying to deliver digitally to most of the theaters to protect from content getting stolen and showing up on the internet before it gets to the theaters. So a lot of them are looking at definitely the 8K types of technologies to power our theaters going forward.
Epoch.
Epoch? EPON? Epoch.
That's a
Ethernet PON over coax?
Yep, exactly.
Ethernet PON over coax. Ha! The PON passive optical network. 802.11ac. Well, the AC doesn't really stand for anything.
Well, it does. It's the designator for the next generation
But they don't
of.
go A, B, C, D. I mean, it's really weird. Like
They-
the one
they
before
don't-
AC is U. It's true.
They don't, but in the 802.11 standards making body, they do assign those to new work groups as they come out. And AC, most of you probably have heard of 802.11g or 802.11n. That's the Wi-Fi that we all use at home and at work. 802.11ac is the next version of Wi-Fi that'll start to come out for consumers. In fact, I think the latest Apple devices actually already implement an 802.11ac client. Great thing about 802.11ac is it only works in the 5 gigahertz band. Somebody was talking about unlicensed bands earlier. It turns out the 5 gigahertz band is a lot cleaner than the 2.4 gigahertz band that everybody uses today for Wi-Fi N and Wi-Fi G. Part of the reason it's cleaner is because there's a lot of devices in your house that already use 2.4 gigahertz, the most notable of them being your microwave oven. So, you know, your microwave oven is sitting there emitting around 2.4 gigahertz. Baby monitors, cordless telephones, all of those things. At 5 gigahertz, the spectrum's a lot cleaner, which means you get a lot better efficiency, you get a lot higher throughput rates, and you don't have to worry about loss due to ingress.
There's also a lot more spectrum at 5.8 over 2.4. At 2.4, you really only have 320 megahertz channels. At 5.8, and it depends whether you're talking internationally or domestically in the U.S., you probably have 13, 14 different 20 megahertz channels that are unique. And it basically is like DOCSIS 3.0, where you're bonding a lot of the channels. So you can bond multiple 20 megahertz channels, and that allows you to get a lot of the higher speeds.
It also has something called beam steering, which is interesting. So.
Beam bending or beam steering. Let's do RDK, Steve.
Mr. RDK.
Mr. RDK.
So RDK stands for Reference Design Kit. In the world of hardware, we've relied on what are called reference designs for years. Basically, someone who builds a silicon platform like an Intel or a Broadcom, when they introduce a new chip, they'll actually give it to us on a board that they call a reference design, and then we work to turn that into a set-top box. Well, in the past, we never had a full reference design of software. There were software specs like OCAP and things like that you might be familiar with, but we never had a full implementation of the software that was actually going to run on a set-top platform. And so a couple of years ago, Comcast set about building a reference design for software. So it's basically the entire stack of software that you need in order to run a cable box, all the way from drivers up into the user interface layer, bundled that all together and started to make it available as a community source project so that set-top vendors can take that reference design of software, marry it up with the reference design of hardware, and essentially have an industry standard cable box ready to run.
OBFDC.
Out of band.
Out of band forward data channel.
Yep, Steve.
It's the carrier that we use actually on a lot of the legacy hardware to carry data down into the boxes, things like guide data and channel lineups and things like that. transmitted down across the cable plant into the set-top boxes.
Okay, how about CCAP? I have a weird way of describing CCAP if you want me to do it.
I'd love to hear that.
Yes.
Okay, I gotta hear this.
Okay, so this CCAP stands for Cable Converged Access Platform, and it has to do with these QAMs, these QAM modulators. So QAMs grew up. QAMs are what people use to convey information from one point to another. The video QAMs came first because digital set-tops came before, cable modems came before voice over IP. So this whole vendor community emerged around making video QAMs. Park that, that keeps going. They keep cost reducing, that's going on. Then cable modems happen, and they need QAMs to get stuff from here to there. And an entirely different vendor community goes around it to make data QAMs. And they keep going along. That was like, what, 10 years ago, cost reducing. But video guys are still the cheapest. Then voice comes along with similar vendors to the data guys, but they also have their own QAMs. And so the people who run the systems are like, every time I turn around, I have to buy another QAM. Can't you make a one-size-fits-all QAM? And that's how CCAP.
Was that Mario or Luigi?
So that's what CCAP is, a way to make a one-size-fits-all QAM that does video, voice, and data.
As a very good explanation.
I would just add one other thing.
Not that
to
weird, by the way. That was pretty good.
Well, the image
That is a pretty good explanation, but I think the other thing you have to look at on CCAP is
Thank you.
As we are expanding our high-speed data offering and still our video offering, because we're adding more and more HD content, everyone at the edge of our networks, we are adding so many QAMs now. We're running into a space and power issue. So another important thing CCAP is trying to solve is space and power, because we are, if you combine all of these into one box, and the technology is allowing us to do that now, out of one spigot you can generate, from 16, some vendors are talking about 96 QAMs out of single devices there. So it's going to help us a lot in our, what we call internally our critical infrastructure, which is buildings and power.
I think another aspect is all these comms now are fed generally with Ethernet, with gigabit Ethernet. And so there's an ideal that we're striving for where you would wire up these QAMs one time, and then if you need to shift things around, you're going to do that virtually. You're not going to have to recombine things, rewire things every time we make a change to our architecture. So wire it up once, and then everything's done from a keyboard after that. That's another vision of CCAP.
And Jay, what's the acronym for that?
What CCAP stands for?
No, for the network.
Wiring once and forget. Wire once and forget.
Then do it from the keyboard. SDN, software defined networks.
Oh, yes.
Is that so?
Ermi? And Bert?
Yeah, he's that guy that lives with Bert.
ECN.
What?
ECN.
ECN?
ECN. Yeah.
Engineering change?
Did you say ECM?
ECN.
ECN.
Doing Ermi or ECN?
Not engineering change
Yeah,
notification.
ECN is used in a lot of the cable labs processes for changing the specs.
Elastic Cloud Network.
Oh, right. Amazon.
Elastic clouds.
IMS?
IP multimedia subsystem.
Wow.
And it's kind of the next generation of soft switching and converged services between voice and data, and between voice both fixed and mobile. It really kind of breaks apart a lot of the functional areas that formerly were done in a soft switch, to provide voice services, whether it's in the cable business or the telephone business or even in the mobile business, into discrete different platforms that handle different functions, control function, or the actual bearer channel, and switching the call and conversation and data channel.
All right, Hotspot 2.0, let's stay with Tim.
Oh man, I'm not a Wi-Fi
Oh,
guy,
I can do it.
but
like
anyway,
one
there's a lot of Wi-Fi stuff.
I'll do it. You know
But
what it
anyway,
is? It's
I'm a
Wi-Fi
Spectrum
with-
bigot. I like Spectrum and Wi-Fi. No one owns a Spectrum. But anyway, hotspot is.
Tim, I got it. It's roaming for Wi-Fi. That's what it is.
Roaming
So,
for life.
so you don't have to keep logging in if you go from one place to another. You're logged in. So all that stuff transfers with you behind.
See, the other thing is on Wi-Fi, there's no revenues with it, and I like businesses that have revenues with it. Wi-Fi is free, so.
Okay.
ATC, Alpha Tom Cat.
Alpha Tango Charlie.
Okay. We'll go with that.
American Television and Communications.
Yeah, right. The
what?
precursor to Time Warner.
Hit us, what is it?
Ancillary terrestrial component for satellite networks.
Okay.
Okay, you're on this
We're
panel
cable
next year.
guys.
I'm gonna do satellite.
Satellite guy.
Yeah, it's the ability for a satellite company to both use the spectrum terrestrially based as well as from the satellite. So a lot of MSS mobile satellite service companies went to the FCC and tried to get it allowable to use the spectrum not just from the satellite but also for terrestrial. And
Haven't heard it yet.
yeah, that's it.
Yeah, we're giving up on that one. Okay, who wants to hear about Shannon's Law? Yay! All right, so you've heard about Moore's Law. Every 18 months, capacities double and cost remains the same. Claude Shannon was a guy who predated Gordon Moore by, I don't know, a couple decades. Yeah. And he did this, he figured out how to find the maximum amount of crap you can push through a wire.
We call that capacity.
It wasn't. It was.
It's a big deal, though. Shannon's Law is going to
channel.
become more and more important as we have more things in our lives that want a connection. So, I would say it better than I did.
Well, it's really information theory, and it gets quite technical. But yeah, how much information can you convey out of a signal or piece of spectrum? So.
Same thing.
In a noise environment, in a noisy environment.
Right.
And it's interesting because there are equations that govern all that. You can take the parameters of the channel and actually figure out the theoretical maximum amount of information you can push down that channel. I don't think we're anywhere close, right?
No, actually, we're getting pretty
getting there.
close. Because I was going to relate it back to the OFD with LDPC. If you look at LDPC, which is an error correction, some people think it's new, but it's actually been around for years. It just was never cost efficient to implement it because you need a lot of processing to do it on real-time communications. But when you apply a lot of these buzzwords you're hearing, people are actually getting close to the Shannon limit. So you can't put more capacity in a channel than the Shannon limit, but you can get pretty close. And that's what these technologies are allowing us to do. They're basically making our pipe more efficient.
And the key is on doing it in a cleaner channel. So, like our DOCSIS goes 256 QAM, which is the modulation format, and you can put a lot of data down that, but it's only you can operate in 256 QAM in a certain signal-to-noise ratio. And so, if you can improve the signal-to-noise ratio and have a cleaner channel, a cleaner cable network, then you can go from 256 QAM to the new version that DOCSIS 3.1 is going to use, which is a higher modulation scheme.
All right.
Why do some people believe OFDM circumvents Shannon's Law?
It doesn't.
Circumvents Shannon's Law. All right, let's thank this panel.
Thank you.
Good to see you again.